Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about a case study on VR output devices. Here the topic is Immersive Virtual Reality Visualization Display Systems. Okay, first of all, we are going to discuss about VR system architecture. In this VR system architecture, it includes VR engine, software and database as input and output, and also we have IO devices, and we have user and task. Okay, here the human senses, it needs specialized interfaces like graphics displays for visual feedback, 3D audio hardware for localized sound, haptic interfaces for force and touch feedback, interested in smell and not in taste feedback. Okay, here the graphics display is a computer interface that presents synthetic world images to one or several users interacting with the virtual world. See here, in this graphics displays, human stereo viewing, personal displays, large volume displays are included here. This large volume displays, it includes active glasses, workbenches, Microsoft Surface, caves and walls. Here in this human visual system, vision is the dominant sensorial channel. Here the depth perception in mono images is based on occlusion. One object blocks another from view on shadows, textures and motion parallax. Here the closer images appear to move more than distant ones. See here, the depth perception in stereo is based on stereopsis when the brain registers and fuses two images. Image parallax means that two eyes register different images, horizontal shift. The amount of shift, it depends on the interpupillary distance. It varies for each person in the range of 53 to 73 millimeter. It works in the near field to a few meter from the eye. Okay. See here we have the output devices block diagram. In this we have IPD, convergence angle and 180-degree field of view, and also we have fixation point A and B. Here we have left eye image, right eye image for image parallax. See here the output devices, same principle used in new 3D HD TVs. See here the left eye image, right eye image, and how beautiful and effective output is. See here. Okay, then we move on to the implications for stereo viewing devices. It need to present two images of the same VR environment. The two images, it can be presented at the same time on two displays, HMDs. The two images can also be presented time sequenced on one display, active glasses. The two images can also be presented spatially sequenced on one display, autostereoscopic displays. Okay, here in personal displays, a graphics display that outputs a virtual scene designed to be viewed by a single user. Such image may be monoscopic or stereoscopic, monocular for a single eye or binocular for displayed on both eyes. See here in personal displays, we have head-mounted displays, 3D binoculars, hand-supported, booms, floor-supported and virtual windows also floor-supported, and also we have auto-stereoscopic displays, desk-supported. See here we have simplified HMD optics model. We have focusing distance, virtual image, and also we have eye relief distance, exit pupil diameter, and we have pixels like A1 and A2, and virtual image pixels are B1 and B2. Next one is about HMD characteristics. Here we have stereo or monoscopic resolution and field of view horizontal as well as vertical, and we have to concentrate on both weight and price. See here HMD integration in a VR system. Here we have consumer HMD and professional HMD. In this consumer HMD we have head adjustment, and in professional we have tracker receiver. In this consumer HMD, here it is a monoscopic VR system is implemented. In professional we have stereoscopic VR system. In consumer end we have RGB converter for color conversion. Here we have HMD tracker control, and in this consumer end we have graphics hardware for view calculation. In this professional HMD we have left eye as well as right eye calculation, and we have two graphics hardwares. Okay, see this one, a perfect example, Olympus iTrick face mounted display FMD200. Here the resolution is 267 x 225. Here the weight is 100 grams. It can be worn over glasses. Next one, here we have the difference between the traditional concave optics with LCD display and half mirror. Here we have free shaped prism LCD display. See this one, a perfect example for Olympus iTrick face mounted display optics. Here the coordination is very perfect. And also we have LCOS display, liquid crystalline silicon display. Here the resolution is 800 cross 600 and the weight is 160 grams. It can be worn over glasses. We have auto stereoscopic displays. In this we have passive and active. Next one is example about 20-inch LCD displays. Here the resolution is 1600 cross 1200 and here the weight is 8.4 kg. Next one is 18-inch LCD display. Here the resolution is 1280 cross 1024. Here the weight is 17 kg. We have holographic displays. Here the objects will appear to float in space with the help of 9 optical layer glass panel. See this one in large volume displays. We have monitor based and projector based. And finally we have haptic interfaces. Here we have touch feedback and force feedback. Here in touch feedback it is easier to implement than force feedback. It conveys the information about contact surface geometry, roughness, slippage and temperature, and force feedback it is very difficult and it conveys information about contact surface compliance, object weight and inertia. Okay, here we have haptic interfaces block diagram. See this one, it shows clearly about haptic feedback. Here see this example. Cyber Touch Glove, a perfect example for haptic interfaces. Thank you.